In this section, we're going to look at infinite limits, and as it states, a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Now, we've already talked about limits that increase and decrease without bound, and of course what was stressed to you at that point was the fact that that would mean that your limit does not exist. So that is what we are still looking at. Alright, so as it states here, it says, be sure you understand that the equal sign in the statement, when you have the limit of a function and you state that it's equal to infinity, does not mean that the limit exists. It just simply tells you how the limit fails to exist by describing the unbounded behavior. So it's not changing anything about what you were told before. If you approach from the left or from the right and it increases or decreases without bound, that still means that your limit does not exist. We're just going to simply describe why it doesn't exist. Okay, so just because we're saying it equals infinity or equals in negative infinity, it still means limit does not exist. Okay. So determine the limit of each function as x approaches 1 from the left and from the right. All right, we're going to look at this both graphically and also numerically to help us figure this out. So we have the limit as x approaches 1. Of course, I have it written here from the left and here from the right with the function of negative 1 divided by x minus 1. Now, if you were to do direct substitution, because if you remember, that's always the first thing that you need to think about. Can I do direct substitution? Of course, if you substitute in a 1, then that's going to give you negative 1 divided by 0. Now, that's not the indeterminate form. Remember, when it's an indeterminate form, that's the 0 over 0, and there is something that you can do to help you figure out the limit, but when it's like negative 1 over 0, that's going to mean that your limit does not exist. Okay, so I know because of direct substitution, my limit doesn't exist here, but we just want to tell why. We want to describe why. Now, you can use graphs to help you out, but we're also going to look at it. Well, what if you don't have the graph? But I've already put the graph on here. So if you were to graph this in your calculator, this is what you're going to see. And of course, the reason why your limit's not going to exist at 1, as you can tell, is you've got a vertical asymptote. So if you want the limit as x approaches 1 from the left side, so that would be this portion of it that you would have to look at, your graph turns and goes up forever, which means it's going to positive infinity. So again, limit does not exist. Positive infinity is just describing why. Then the limit as x approaches 1 from the right, so that would be this portion. But see, this portion of it turns and goes down forever. So from that side, you would have an unbounded behavior that decreases. It goes to negative infinity. Now, I do want to look at something on the calculator here. And this is something that you can look at each time. All right, so I've put this function in my y equals. Okay, so that's what I have here in y1 that we're looking at. Okay. Okay, so let me go. I was wanting to look at the table. All right, what I've done, and I've already filled this in, I put the table in ask mode like we had done earlier in filling in those tables, and I've already substituted in these values. Now, these values would represent this portion of the limit when you're looking from the left side of 1. So I went to the left side of 1, and I started with negative 1, which you've got the graph right here we can look at. So you see that negative 1, your value is a half. And then I went to x equals 0. So at x equals 0, you can see that your value is positive 1. Then I went to 0.5. So 0.5 would come up here with your value of 2. And then I did 0.6, 0.8, 0.9. I just gradually picked numbers that were a little bit closer and closer and closer to positive 1, but on the left side of positive 1. And as I got closer, so I did the 0.9, then I did 0.99, see what your y values are doing. They're just continuing to get larger and larger and larger. Of course, if I came in here, now this is, I'm going to put in 0.999. Now it's going to top over this last one because I filled it up, but 0.999, you can see that it even gets that much larger. So even if you don't have the graph to look at, you could actually substitute values into this function on the left side of 1 and notice that your numbers are just getting larger and larger, so that verifies the positive infinity. I'm not going to take time to do it, but I could do the same thing. Like I could come in from the right side and do like positive 2 and then 1.5, 1.4, 1.3, 1.1. And what you would see happening with your y values in that case would be you should see that they're getting smaller with each one of those. That would indicate the negative infinity. Okay, next one. Now this is still the same set of instructions. It wants you to determine the limit from the left and the limit from the right. But if you notice, I haven't gone ahead and written out two separate limits, like the one for the left and the one for the right. Because if you look at your graph, as x approaches 1, of course, again, that's where you've got a vertical asymptote, because if you were to substitute in 1, you would end up with negative 1 over 0 again. But left and the right here, see, both sides do exactly the same thing. They both turn and go down forever. So your limit from the left and your limit from the right, both being the same, then you could just write it as the limit as x approaches 1 of this function equals negative infinity. I had to keep it separate on that previous example because one side turned up forever and one side turned down forever. Again, these are the same, so you actually could just write it this way.